All right, welcome. I'm losing my voice, so I'm going to really use the microphone as opposed to normally just shouting at all of you. So Flagship 2 obviously is our second flagship project. You can tell that because we numbered it number 2. Nevertheless, this one's focused on spectrum, it says spectrum awareness. That's not right because I didn't fix that slide and Mary didn't catch it. So it's scientific coexistence in the high frontier. We already talked about flagship projects, so we're really, this is for us, Flagship 2 is spinning up where Flagship 1's been executing for a year. And we're really trying to reach across a broad spectrum of the center and engage in very meaningful things. And I have to say, I'm very happy with the flagships, is on both of them, we have hit very relevant areas as things have evolved. So scientific coexistence in the high frontier is really about mega constellations. It's about looking up at them, looking down at them, and we have very sensitive scientific systems. We have radio astronomy with radio telescopes. We have Chris Dupree talked a lot about the existing telescopes, but there's an ambition in the US astronomy community to develop something called next generation VLA. The international community is developing a whole series of very powerful radio telescopes, square kilometer array, and it has a whole series of frequency ranges. And all of these systems are now looking up through satellites, and they suffer from the fact that we would put them in very remote locations precisely to get away from interference. And now, you put a transmitter on a satellite and it's visible over half the planet. And so, or a quarter of the planet. And so, depending on the altitude. And because of that, there's actually no reason to go to the remote locations anymore, almost. It's not quite that bad yet, but I think we're at 10,000 Starlink satellites as of earlier in the week. And we're headed towards millions of satellites. Everybody is going to want to do this. Starship, which is shown in the lower right corner there on the slide, that's going to up the launch capacity a factor of 10 over the Falcon launches. It is going to become something that is very common for companies to go out and launch 100 satellites. They're all going to use communication signals. They're all going to generate unexpected interference. Some of them may even be radars or other systems that are actively using the bands in ways that we're currently not. And at the same time, many of these systems will be in low Earth orbit. So they'll be between 320 kilometers and about 500 or 600 kilometers. Meanwhile, many of our scientific systems like weather radiometers are looking down. They're at 600, 700, 800 geostationary, and they're looking down through these constellations. And, we saw some orbital modeling at various points in the tour. We saw, kind of here's all the satellites. Every one of those is a source of interference that we're going to have methodologies to mitigate. And in some cases, one of the things I think is a theme of Flagship 2 is the scale of the systems we're trying to mitigate really is going to matter. One satellite is not that big a problem to deal with, no matter almost no matter what it's doing. I won't quite say no matter what, because I'm sure we could, set off an EMP and really cause trouble. But nevertheless, one satellite's not bad. A dozen satellites, not so bad. 10,000 satellites is a different beast. 100,000 satellites is really a different beast. At the same time, we have NPRMs that, I'll talk again. And these are very forward-looking by the FCC. On the other hand, we have no ability to evaluate them objectively. What does it mean to allocate 20 gigahertz of spectrum in ways that will be politically decided to use by satellites that are globally visible? What impact will it have on the weather measurements we were just looking at? And, obviously they'll have a lot of downlink capacity, but will they even be able to make a measurement anymore? And we can't answer those questions efficiently. So I'd like to see us with Flagship 2 get some prediction capability, make a step towards it. Look at the rights and coexistence mechanisms. I think a very important thing in rights and coexistence is how are we going to deal with post facto, there's a system and it's at scale and it's causing problems. We haven't seen too much of that yet. You know, we're seeing a certain amount of data flagging, and you saw on Chris Dupree's slide that their beam avoidance mechanism was pretty effective. Is it effective with 10 times as many satellites? I don't know. All right, so we don't know the answers to these things. At the same time, we really don't know the follow-on impacts. So you interrupt these scientific measurements, you disrupt them in sometimes subtle ways, and we don't know what happens to a hurricane forecast. We don't really entirely know always where the thresholds, say in a radio astronomy imaging system, are for it no longer functioning properly. And nevertheless, you know, we're wanting to build next generation VLA for astronomy, and there'd be hundreds of telescopes spanning 1 to 100 gigahertz. And the current designs for that system kind of assume that there's not interference in the bands. And you know, realistically, the engineers building it know there's interference, but the scale of dealing with this is not conducive to spending large amounts of money on a system without a means to ensure that it's actually going to function. So that's the big picture challenge of Flagship 2. It is timely and relevant. I'm actually very happy the FCC is doing these things, because it is, you know, we were on target when we planned this out, and I'm very happy to see we have a team and we can take some steps towards addressing this. One of the things that came out of the Flagship 2 planning at a large scale, from my point of view, is that what we could plan to do in a comprehensive manner is vastly beyond our current resources. But that doesn't mean we can't make some very significant and meaningful progress in key areas and selected areas. And you know, there's questions like, you know, what are the incentives we need for scientific coexistence? You know, can you do this with a minimum of regulation? We have people wanting to deregulate and make everything easy with these NPRMs that have come out. But what are the correct regulations for systems like this? Is the regulatory environment for a constellation of 10 satellites really the same as one for 100,000? You know, I don't think so, actually. Meanwhile, we're starting to build some modeling capabilities. We're starting to do some observations. And, you know, we're entering this era where clearly the country is headed towards lots and lots and lots of space deployments and lots of systems that need RF and also generate signals, sometimes intentional, sometimes unintentional. With that, we have a series of work elements. You know, here I've divided it instead of kind of work packages, but just down at the work element level, because it's a little smaller project than Flagship 1. We've got a radio science coexistence simulator, RISC-SIM. Paul Brenner is going to talk to us about that and the plan for what we're going to be doing with it. It came out of work we did at MIT Haystack Observatory to model the impact of Starlink on the Westford Radio Telescope. We're going to have Angie Cruz discuss scientific system coexistence and impacts. This is what happens to the weather forecast, what happens to the astronomy data pipelines. You know, what does it mean for systems we might build for astronomy? Then we've got John Swoboda to talk a little bit about signature collection with scientific platforms. This is pulling together some of our ongoing data acquisition platforms and efforts that are relevant to this area and trying to use them in a targeted manner to help build capabilities or inform the simulator or even discover what the right questions are sometimes. We don't know, for example, what all the harmonic structure looks like off different satellites, off different ground systems. You know, what is the harmonic structure of 6G cellular with phased arrays going to look like? I don't know. But that's something that we could start to look at because we've got an FP1 phased array and we've got MEPS to measure it. And so experimentally, we could imagine that might be something we could go do. Finally, you know, it's this coexistence incentives and markets, which Prashant is leading and we'll talk about. It's how are we going to actually deal with this regulatory policy and rights that go with this? And it ultimately goes beyond spectrum. It's also the policy and rights that go with mega constellations, which I think at some level are even more complex than the spectrum issues themselves. So that's it from what I was going to talk about. I think next up is Angie. Actually, she's going to start.
Hi, good afternoon. I'll provide you some updates from our work element group on scientific system coexistence and data impacts. So as a spectrum increasingly becomes congested and regulatory agencies are looking at opening up bands for new applications such as 5G, in the future 6G, mega constellations, there's a concern that this may impact and cause RFI to some of our sensitive scientific applications. In part, especially for the low power, for the applications looking at low power signals, so microwave radiometry as well as radio astronomy. So we know microwave radiometry data is really important for our numerical weather prediction models and for our weather forecasting, especially for severe weather events such as tropical cyclones and hurricanes. And on the radio astronomy side, we use our very large apertures in order to pick up low power signals to help us explore the universe. So our work element is a focus on looking at the coexistence between the systems and the data impacts from increased RFI on these applications. So we have three main goals for our group. The first group, looking at microwave sounder data, will provide a comprehensive analysis of weather forecast impact for data denial and biasing studies. Our second group is looking at determining what the science observation potential for radio astronomy will be lost at different levels of RFI in those future regulatory scenarios. And then our third goal is focused on policy, so providing strategic research related to discussions around 52 gigahertz at WRC 27, as well as providing that strategic research around the FCC satellite spectrum abundance. So providing a little bit more background on the weather modeling, we know that the 50 to 60 gigahertz band is very important for a passive microwave radiometers. There's been a previous study by JMA shown on the top left that's looked at the impact of different bands and frequencies, and what they found was that losing the 50 to 60 gigahertz band is a huge damage for that forecast score. So looking at some of those potential causes of RFI, on the bottom right, I show modeled RFI for microwave radiometer observations from 5G cellular networks. So this is a study done in support of WRC 19, and those red spots on the plot is some of that expected RFI. There's concerns that the second harmonics from these 5G signals may actually have an impact on those 50 to 60 gigahertz channels. And then on the top right, I show NOAA 20, which has ATMS on board. It's orbiting at about 830 kilometers. And it's looking through these mega constellations such as Starlink at 550 kilometers. So there's potential RFI from either the spacecraft themselves from the mega constellations, side lobes, as well as from the ground looking up at those and transmitting to those spacecraft, especially if spectrum is reallocated at 52 gigahertz. Okay, so moving on into the weather modeling methods. So our team from University of Wisconsin-Madison is completing this experiment. So they'll be inputting our microwave radiometer data into a new numerical weather prediction model called GFS, or the Global Forecast System. And they're looking at a time period of 6 weeks in 2023. This is an active period where there are 11 named storms. So there's two different experiments under control. So for the first experiment or control, they'll input all the current observing systems during that period. So this will simulate current operations. They'll then run their data denial experiment where they'll deny the microwave radiometer observations from 50 to 55 gigahertz in AMSU-A, SSMIS, and ATMS. And those bands and frequencies are shown on the right. And then for the final experiment, we'll look at biasing of that data. So we will create a model for RFI, and that RFI will be added to those microwave observations in the 50 to 55 gigahertz bands. And then we'll run that data through the numerical weather prediction model, and we'll see what the results show from that. So next up, for the radio astronomy group, we know that mega constellations are a pretty big concern for their group, based on research that has shown that there are unintentional emissions from these spacecraft. We also don't have very detailed measurements of the spacecraft's receivers and transmitters. A lot of that information is proprietary, for instance, for the SpaceX spacecraft. There has been some modeling work done at MIT Haystack. So looking at the power levels from the Westford Radio Telescope, shown up here in the middle. So this is going to be really the backbone of the RFI modeling that Paul will talk about later for RISC-SIM. And this will allow us to study the impacts of those mega constellations on the radio astronomy. So the methods for the radio astronomy work, the team will first identify and obtain a data set for testing and simulation. They'll then define what the science observation deliverables are so they can assess that for degradation due to RFI. They'll then simulate RFI using RISC-SIM, and then that would be applied to the sample data set. And then the team will be able to report any quantitative or qualitative change in that science data quality based on the metrics. The main policy driver for the astronomy team is the FCC proceeding satellite spectrum abundance, which we talked about in the panel this morning. And the radio astronomy team is mainly focused on W bands. So that's the impacts from parts of the 92 to 114.25 gigahertz. So our last slide here is on RISC-SIM integration. So Paul's going to be talking in more detail about RISC-SIM next. But RISC-SIM is going to be key for our team to model the RFI so that we can provide our analysis of what those effects will be. So first of all, from our for radio telescope looking up, we'll need to model the predicted RFI contributions. And then for the microwave radiometer looking down, we'll have to model the different sources of RFI for that as well. Some examples would be for the 5G second harmonics, as well as uplink from Earth to LEO, and then this LEO constellation side lobes. And then those RFI contributions will be added to the actual observations, and we'll be able to provide some quantitative analysis on the impacts. Just a quick comment on some risks and dependencies for the weather modeling group. We are taking a look at if we should include the 57 gigahertz channels as part of our work. So we are waiting to get a response from Jordan Girth to help us decide if we need to include those channels as well for our analysis. We do need a decision by the end of November. And then one of our other kind of dependencies is just that we need to run the control experiment first, so we'll take 6 weeks, and then run the denial experiment, and then the biasing experiment. We will need the RISC-SIM RFI model in order to run the experiment number 2. And then one of the dependencies for the radio astronomy group as well is really getting that RISC-SIM model of RFI up and running so that they can use it to conduct their experiments. Right, and that's all I had. Thank you.
All right, are we ready?
Yep, we're all good.
Excellent. Well, I'm Paul Brenner, one of the directors of the Notre Dame Center for Research Computing. It was great to meet so many of you in person yesterday, and I'm privileged to talk about what we've started here in Flagship Project 2 RISC-SIM simulators. So if we can go to the next slide, please. So ultimately, we want to leverage, the ability for these predictive analytics through physics-based simulation, right? And trying to build a tool that will capture for the community the majority of the challenges that Angie has just discussed, that Frank has just discussed, and make it quantitative so that we can provide this to the policymakers in all of those primary impacted areas. The top 3 goals for year 5. So the original sort of model we started came out of MIT Haystack, very effective, but we wanted to add additional capabilities. We also had to migrate it over to Python so that we could have a larger development community. It was originally written in Julia. We wanted to do realistic simulation of a larger number of constellations so that we can scale it out for performance reasons. And then we want to make sure that we have both educational and research components to it. So we want to have a number of interfaces, whether that's through a Jupyter notebook or through scripted API, and build this so that it's a robust tool used in both of those cases. We want both classroom use and actual lab use. Team-wise, Samuel Thie was the author of the original version that came out of MIT Haystack. DK, who's there, is the lead software engineer on the project out of the University of Notre Dame. Prashant and Song both have been participating in terms of testing and their graduate students giving feedback. And obviously we appreciate this initial support through Flagship Project 5 and the National Science Foundation. Next slide, please. Okay, so specifically here, and Angie mentioned some of this, so this is existing software at this point, and we were really excited how much we've been able to sort of push it forward in the past 3 or 4 months, but it can do the scientific instrumentation, ground emitters, satellite constellations, and we'll show some examples of this, but so it's not just theory, it's not vaporware, this is software that we'd love all of you to start leveraging and playing around with. The example here that was mentioned in the Westford antenna at MIT, observing astronomical objects, specific satellites, so that we can measure various signal strengths. You can get a general workflow there in the bottom, right? So if you can enter in your configuration files, create the antennas that you want to model, define the various link budgets and satellites. The simulation runs DK. We had this running yesterday afternoon at the poster presentation. This runs on the order of minutes, and as we start to add more, we will continue to add multi-parallelism for greater scale. But if anybody is looking to do this in the near term, this will run on a laptop. So we're working to scale it up so it'll run all the way up to many core servers, up to HPC systems. But again, for the educational purposes, we want something that an undergraduate student can run as part of their coursework. Next slide, please. Just gives you a general idea here. And again, we'll have the links on the coming slides, so hopefully people can look at and play with it. There's a core simulation engine and the things that are implemented at this point. So we have satellite orbit modeling for predicting satellite trajectories, link budget and gain modeling that counts for the free space path loss and antenna gains. The coordinate systems, transformation between ground and beam coordinates. I'll talk a little bit more about the coordinate systems. As Angie mentioned, we're going to have a transformation so that we can have sort of the ground facing and then we can have the space facing. Currently, it's focused primarily on the ground facing. And then the realistic modeling effects that we've been working with the teams as far as Doppler, transmitter character, and environmental effects. Next slide. So again, I mentioned 2 tracks as far as the software build out. And we see in the graphic here, you see sort of how we think about the community of the developers in the space. So the core computational backend, again, I mentioned, is in Python for performance. Obviously, Python's wrapping a lot of C libraries. We'll have everybody be able to pull and collaborate from the SpectrumX GitHub repo via their particular development environments for our software development team. And then the end user will have the scientists and the undergraduates. And today what is implemented, there are Jupyter Hub notebooks for undergraduate and for some of the scientists, if they prefer that interface. There's a number of templated examples for the different feature sets so that people can go in, pull up one particular Jupyter notebook and understand the computational capabilities that are already in the software under the hood. And then there's the core sort of Python API so that you can call this command line so that if you wanted to, you can interface it with, say, a weather model such as WRF or one of the other computational simulation packages. And those are the 2 ways that we're building it out at the moment. Next slide, please. Okay, software repo, please, and we have a QR code on the last slide, but to understand how you get through the interface of those tutorials, through the course source, computational package, and the rest of them. And again, you've got the predecessor there from the Julia code. For those from a retrospective, we want to make sure we keep everything for general fair use of all the data. Okay, next slide, please. Okay. So priority areas and what we've already accomplished. So 1, we've already accomplished the conversion of the Julia to Python. The Doppler effect prediction is completed. Detailed transmitter characteristics, advanced propagation, environmental effects, direct aggregate effects modeling. Things that DK and team are working on right now are advanced receiver models, ground-based emitter modeling, And then in recent months, as Angie was discussing, we really want to understand better which aspects of weather modeling that we need to do integration with in terms of prioritizing. There's a whole lot of interest. It's just prioritizing what we have and at this scale of funding and looking for additional funding to grow that. And then I mentioned the bidirectional reference frame modeling that will need the geometric sort of interpolation so that we can look from the other direction. Next slide, please. So a couple of examples here. And again, please talk with DK. They're in person and pull down the code. But a number of these opportunities for immediate visualizations from telescopes and satellite antennas. Next slide, please. Okay, total power, time series, frequency plots. Next slide, please. Sky map, a number of these were on previous, I think both in Frank's and Angie's slide, some of these sky map with respect to power and the satellites. And I think that gets us to the very end. For those that later want to watch, we've also got a demo of running through the code set. QR code there will take you to the GitHub repo. And the thing we ask the community for is please download it, speed it up. One of the great things that we have this opportunity with Flagship 5 is that we have software developers that are available to help add features, fix things, make things better for you. If there's additional functionality, if there's different ways you'd like it referenced, the way we input individual configuration files, speed, performance, please, give us your wish list, kick the tires, and let us know so that we make this as productive as possible for the community in Flagship 5 year 5 or Flagship 2 year 5. And with that, any questions? Maybe we'll take them at the end.
Questions at the end? Questions at the end?
Yeah, at the end.
Okay. Yep, so I have been told that we'll do questions at the end. So we'll pass it off to Prashant now.
Hi, good afternoon, everyone. I'm Prashant Krishnamurthy. I'll be talking a little bit about the coexistence rights and initiatives rights and incentives that we are looking at in Flagship Project 2. Next slide, please. So Frank, I think, kind of alluded to this in the beginning when he was describing Flagship Project 2, and today's morning panels were so excellent. They actually gave us a good idea as to why this is an important problem. We cannot look at the coexistence, the spectrum rights, and what incentives will actually work in this high frontier, because they are very different from the traditional models that we may have used. There are many different models, but we have used these for terrestrial communications and sensing and federal use and so on. But these are very different for the scientific coexistence in the high frontier. Please click. So since the last center meeting, of course, it's been only a few months since this work element was created. We have tried to integrate this work with the RC, economics, policy, and rights groups, because most of us are there. And we have been brainstorming on different rights models that might apply to this, to the scientific coexistence. There's a position paper that Dongling has written on receiver-oriented rights, and there's a TPRC paper that Ilya has written on landscape rights. So these are the two of the rights models that we will be looking at. I'll speak a little bit more about those in the coming slides. The other people who are involved, of course, are lots of our senior folk, people like Mike, Randy, Igor, and Federico Bobbio from Northwestern, Songshen from UVA, Nick and Monisha from Notre Dame, and Tom from Clemson. These are all the people who are involved. So the three models that we are looking at in terms of rights are the receiver rights, as I mentioned earlier. This is probably our thinking at this point is that we can tie it more closely with the risk sim, because the risk sim is looking at, for example, the receive antenna on the ground, and also the satellite antennas when you're looking up. And so understanding the receiver rights using the simulator seems to be a natural progression for us if we can get there. So that is one of the ideas we're looking at. The second rights model that we are looking at are the so-called landscape rights and property mismatch. So this is looking at scientific applications from a landscape perspective. In the morning in the panel, for example, there was a discussion of how different agencies in different countries are sharing data about, for example, the ocean temperature in order to predict hurricanes. So this is a landscape. This is not rights that are restricted to a particular frequency band, a particular geography, a particular nation, or authority. So we have to think about what kind of spectrum rights need to be in place for us to accomplish the goals of these scientific applications. The other approach that we are thinking about is to look at the work that Angie's group is doing on data denial and data biasing. And these things have impact on the quality of the results that we get in the scientific application. So the question now becomes one of how can we think about spectrum rights in the context of the needs of the application. So will the application be affected by certain problems due to data denial and data biasing? If so, how would that translate back into spectrum rights? Next slide, please. So at a high level, all three of them have some kind of overlap, but I just want to give a sense of why they're a little bit different from the traditional rights models. In terms of the receiver rights, we are looking at the interference at the receiver, which hopefully the risk sim will help us understand better. This is not transmit power oriented, but more at the receiver level. So but also the applications do not have the same characteristics. Some receivers are very sensitive. Defining harmful interference is not easy. We have to get feedback from the receivers, perhaps, to say if something is going wrong. And then there are transaction costs. Already Starlink is working, for example, with some of the scientific applications to help steer their beams and so on. But as Frank mentioned earlier, it's not clear whether this will scale to tens of thousands of satellites in the future. Also, as the receivers become more and more sensitive and there are new receivers that are being built for scientific applications, it's not clear how these things would change. I already talked a little bit about the landscape, right? So there is a landscape of spectrum that is used. For example, the 50 to 60 gigahertz that Angie was mentioning is one component of the weather modeling. So there are many different pieces of spectrum that need to work in some kind of quasi-synchronicity, if you want to think of it that way, in order for a scientific application to do what it needs to do. So we have thought of a few different ideas here. So you can typically spectrum rights have been parcelized. So they are parcelized either in time, in geography or in spectrum, and also sometimes in time. So in property rights literature, there's the approach of looking at easements in parcels, or we can look at overlay rights where there are no parcels really. Again, because of the sheer scope of the mega constellations, I think there are challenges that we don't understand very well yet, and we are looking at that. And finally, the application rights, where the scientific application needs really good data, and we really need some nice models which will tell us how the spectrum rights would impact the quality of data. And I don't think we are there yet as well. So these are the three ideas that we are examining in this work element. Next slide. So in the longer term, I think there are other questions that we would like to answer, but these may get moved to later. First of all, how flexible use rights would matter in the case of scientific users. So for example, if we have a certain amount of spectrum, the rights are allocated for a scientific application, is it possible for these slices of spectrum to be used elsewhere? There are also advances in other fields which may impact how scientific applications will do things in the future. For example, there is the use of AI and machine learning, which could help address some of the data biasing and data denial problems, perhaps, if they are correlated pieces of data that the AI can understand what the problems are and take those into account. Again, we talked about how receivers are going to become more and more sensitive and advanced in the future. So these could lead to other kinds of challenges. And we also have to look at what kind of incentives and market mechanisms may allow better coordination and coexistence. So right now, the coordination between, for example, Starlink and others are happening pretty much on some goodwill. And the question is that as the market becomes more congested, there are more players. How can we incentivize these kinds of coordinations to happen? Next slide, please. So what we are doing right now is looking at the code that Paul talked about, to understand the inner workings of the risk sim. Looking what can it do when we are looking down from space and we are looking up from the ground, and how we can use this data towards understanding the rights. One of the challenges that the rights questions have is there are many different kinds of impacts that these mega constellations will have. There is in-band interference, out-of-band interference, this aggregate interference. There are harmonics, which are coming from bands where we did not even think of controlling the rights as it pertains to scientific applications. So how do we map these things to rights is a question that we are trying to look at. Now, Ofcom introduced this spectrum use rights model once upon a time, and in the last year or so, there is some interest in the so-called evolved spectrum use rights. This seems to be at first glance similar to receiver rights, but it's not clear how this would apply to the high frontier, so we are examining that. The last thing that we would like to do, but we haven't made any what should I say, even incremental progress perhaps in this area, is to look at the experimental work that John is going to talk about next and see how we can use the insights from the experimental work to develop some kind of an abstraction or model that we can use for how spectrum is being used in time, passes, time, area, and spectrum, how they are being used for the scientific applications in different areas, and how they are being affected because of the mega constellations. So hopefully the experimental work will help us also to use some models in understanding the rights better. And that's all I have for today. Thank you.
Hi, I'm John. I'm going to be talking about the signature collection and all the data collection that Prashant mentioned a minute ago. So this is like the high level overview here. This is it's very high level because again, when we start getting into our experiments, we always find we have to iterate. We're always going to have to be bringing in new information. Did we set the experiment up right at first? You know, what new information have we got and how do we adjust? So we need to be pretty flexible. And so our main thing here is, you know, we'll develop our experiments, collect data, but the main thing is to, you know, one of the main things to collect data for validating portions of risk sim, really. And that is a huge driver with this work. The other thing in the end, we want to make sure the data we collect is useful. We want to make sure also it's well annotated. We want to have at least a basic standard of how we get our data and what is available for further analysis. You see a lot of people in the AI ML group trying to come up with better ways to annotate data and having certain standards that they want there so they can do further analysis even after the fact of our original intent. There's always a chance you can go back and find interesting things. You know, do we have it? You know, we would like at one point to make an interesting things detector, which I think I've taken that from Frank because
Flagship one, John.
that was So we can test the interesting things detector with this data. So we have all these great tools now. So again, we're driven by all the other requirements from the other group, from the other parts of the work elements, the risk sim validation, the impacts on the scientific sensors. How do we try to measure that? Angie will be, you know, probably coming to me asking if we can use things at Haystack. Can we use Westford? Can we use a 37 meter? You know, and you know, I'll be also relying on Maria to get more information about harmonics. How do those, you know, how do those harmonics affect maybe our predictions for risk sim? You know, can we build some of that in there later on? And also policy impacts. How can we help, you know, develop? Can we simulate regulatory models maybe within our experiments maybe? And I kind of want to just, you know, throw these questions out there for people to kind of then come to me later, like, well, could we do something, you know, along the lines with, you know, at, you know, Haystack or Westford, or maybe with the mobile radiometer platform that Al has been developing. And, we're going to try to use all of the different systems we have available to us right now, and including the MEPS too, if we can, for certain places. For example, we can possibly use it with our 37 meter antenna. We have the downconverter architecture that can get it down into the band that the MEP can sample. That would be very useful and a very nice thing to have, to do other studies. Actually, I just got a request today from a group who wanted 37 meter data for another set of experiments they're doing. So now with some, I also want to just say to Paul, yes, this does work. I downloaded it, and as I was putting the slides together last minute, I was able to make this image very quickly. So good job. And awesome. So right now, I think we want to target just a few main systems we have here with this to kind of do some validation here. Our Haystack Westford antenna, the MIT Green Building dish that on campus, and also I've been talking with Ali. Was very interested in working with the SSEC further, and so can we, do some work with that? We have, what type of emitters can we put into your Starlink 6G? But can we go further? Again, this brings in some things that Maria has been working on. Can we bring in information about harmonics to maybe advance the types of receiver models we have in here? And again, we can use things like her hunt for harmonics in the wild, and can we use maybe some of our own systems we have here? Could we create a MEP setup that could do some of this harmonic analysis here? And we can go. We've also talked with Al. There's been some ideas floated around by using the weather radiometer band to do some of the harmonic analysis as well. But the big so this is just one sort of set of experiments we can do with it. And then Al was gracious enough to talk more about the next couple of slides. Al, are you there?
Yes, John. Thank you very much. I appreciate the introduction and the background as well. And I don't know if John was referring to what we're doing as the interesting things detector, but I have a feeling it's de facto going to become that way. Let me first describe what the background is of why we're doing this interesting things detector, so to speak, this mobile radiometer van. And it begins with this density of interferers analysis. This will be the only equation we present probably this week. So, but I want to point out that using nothing more than the Friese formula, one can come up with a simple product of density of interferers times the power transmitted by each interferer times a coupling factor that has to be within a certain limit, depending upon just how sensitive our weather radiometer is, depending upon what its permissible received interference is, in order to coexist. This delta T nominally is thought about as something like 50 millikelvin in many of the work in ITU documents. Frankly, it is really more like around 10 millikelvin if we intend to do climate quality measurements in the future. Now, this coupling factor is also important because this coupling factor pertains not only to scattering of radiation from terrestrial sources that are building rooftops, for instance, trees, etc., but also you could think of that as the antenna gain of an upward transmitting satellite control signal or satellite data signal. So as we start looking at coexistence in the, for example, 5 millimeter band, 51.4 to 52.4 gigahertz, this pertains to the spectral abundance issue, we have to recognize that C now becomes a gain, not a loss factor. Next slide, please. Now, we set out about a year, almost 2.5 years ago, actually, to see what we could see with an existing radiometer system called the polarimetric scanning radiometer. And I built this back in the 90s, and we refurbished it to study what was being emitted in the Denver area, just a local excursion we took, in the area near 23.6 to 24 gigahertz. That's this important K-band range that's used for water vapor estimation from satellites. And we did see interferences. We have these what we call O records, which are PPI scans of the radiation field. And there are times when we saw excursions in our O records that were many hundreds of Kelvin off scale. Now, these kinds of RFIs could also be attributed to the fact that we didn't have necessarily the best filters in the world. These filters were of circa roughly 2000 era. And even since then on ATMS, those filters are a little bit tighter. They're also starting to get rid of some of the bandwidth that we could be using by virtue of their tightness. So in order to do a more, what we call a traceable study, next slide, please, we embarked on building what we call a hyperspectral spectrometer assembly. We have two now hyperspectral spectrometers, one at V band and one at K band, and the frequency ranges they cover are listed above. And those are now being built, they're being assembled. You can see one of our students, Duke, in the laboratory, in the clean room, assembling that right now. Each of these has spectral capability of around 1,000 spectral channels instantaneously with 2 megahertz bandwidth. Integration times of roughly 45 milliseconds. The upshot is that we're going to have traceability and sensitivity that far exceeds what you can get with SDRs, with software-defined radios. And in addition, these systems, these radiometers, these spectrometers, they have high gain antennas. So we're going to know where the radiation is coming from with an additional roughly 20 dB gain. So when you look at that between the 20 dB gain roughly and the 30 dB traceable sensitivity, we are far exceeding what can be obtained with what I'd call typical spectrum analysis equipment. So next slide, please. And what we're doing is we're now installing that in our van. Sometimes we refer to this as the bandwagon van. The mobile radiometer platform is another name for it. And this is basically a 9-passenger Chevy van that we have retrofitted. We have cut a hole in the roof and put a frame in the top and are going through everything needed to make sure that this is a roadworthy platform. And when I say roadworthy, I mean we have to be able to say that after several thousand miles of driving and visiting various different cities and what have you, that we have had no incidents. Nobody gets hurt in any way. A lot of what I'm doing to this van follows directly from my experience in flying with NASA on their aircraft, ensuring that safety is number one. Science is then number two. And so we're making sure that with regard to our instrument, that we're going to have traceability down to the 0.1 Kelvin degree of precision in these two important spectral regions. And you can see the cities that we're hoping to be able to visit. We hope to be able to also stop by at various institutions along the way and provide demos of this technology, as well as additional seminars, talks, for instance, on what we're doing, why we're doing it, and the importance of spectrum in passive remote sensing. So I'll turn it back over to you, John. Thank you.
Thank you. Yeah, so I will likely see you in Boston. And so but basically, for these are just some of the ideas for experiments. I kind of just wanted to throw out, hey, what are we missing? What other ideas do we have? What types of experiments are we missing? I know I've talked to others. I've talked to people, again, I want to just bring back to LE, talking about interference tests with the SSEC. And can we do, maybe some more, experiments involving new sort of economic models for spectrum management, that too. But again, very open to ideas, and I'd like to hear them. So thank you.
Workshop.
Yes, in the workshop tomorrow, we'll be discussing all of these. So why didn't it show up? Anyway.
I don't know.
All right. Anyway, yes. All right.
I think we have a little bit of time for questions.
Mm-hmm. Yeah.
Do we have questions?
I have a question. Is there a way I can ask in the audience?
Yep, go for it.
So it's not really a question, but I just want to actually make a comment. This is Rick Reese on the External Advisory Board. So when this project was kind of coming together maybe 18 months ago or a year ago, I really had my doubts, but this is what you're doing is amazing. I mean, I'm just blown away by how organized it is and how well you're doing. I just want to make that comment because I was wondering where this was going when it started, and now I think I have a really clear path, and I think you guys know what you're doing.
Thank you, Rick. I really appreciate that, Rick.
I have a question about the risk sim framework. So I might have missed this, but when you say there's like two types of educational tutorials for synthetic data and real data, is the real data like live time data or pre-recorded data from Haystack?
We're hoping to incorporate pre-recorded. So I'd like risk sim down the road to go beyond simple flux models. Which right now we characterize a transmitter by how much energy it's putting out at a given frequency. We're going to extend that to time-dependent models, for example, of the emissions. I would like to get it so that we could take data from, say, a MEP or the weather radiometer van and actually fold that into the simulator and have kind of empirically driven simulations. Additionally, there's going to be need to mature the selection of link budget models because you can both do kind of direct physics modeling as well as you can do things that you want to be statistically accurate, like clutter modeling, for example. And that's some of the stuff we've been talking about. There's been discussions with the Notre Dame team about some proposals related to this, because one of the challenges for Flagship 2 is when you look at the big problem of scientific coexistence in this very rapidly evolving world, it's of such scope, even relative to our center's resources, that we're having to be very selective about what we pick out and target. And so we've tried our best to pick things that would be impactful and fit together, but there's so much more work that can be done here.
Renee, up next.
Renee, you're muted. You're muted, Renee.
Wow, I pressed unmute, but okay, all right, now it's working for real. I am basically a consultant to SpectrumX on policy and contributing to Flagship 2. Wanted to actually ask Prashant a question about his presentation. Inside of the meteorological community, when talking about a number of these passive challenges, there is a concept which has been noted in a number of different papers as well as in a number of filings referring to insidious contamination, specifically insidious contamination of specifically interference which is difficult to perceive, large because it looks just like a regular observation. Specifically a sort of atmospheric observation, but it's not actually a natural emission. It is actually interference. One of the concerns which was raised inside of our call, together with the European Center for Medium Range Weather Forecasting, about a week ago, who really has a great deal of expertise in these questions. One of the questions raised was sort of, okay, so how do we perceive this difference between the sort of more obvious contamination versus really this insidious? My feeling about really the sort of economic analysis is that you sort of need to have a real clarity, sort of black and white sort of observation as to whether it's contaminated or not. But we don't necessarily have that reality inside of really the meteorological community. How are you thinking about dealing with this as you're thinking about your overall analysis?
Thank you, Renee. This is great feedback. I think looking at the three models that we are considering in our group, the receiver rights model is the one where this is going to have problems because it's going to be very difficult to define what is harmful interference if you even don't know what is insidious, whether it is really interference or if it's a real observation. But I think hopefully when we are doing this data biasing, data denial, maybe there is some kind of a hope that we can extract information about what is happening to the scientific application itself, and why this insidious behavior is being observed. So where is it coming from, and how is it impacting the application? And if you can have some kind of, I don't have a good answer to your question at this point, which is we need to understand that better before we can translate it back into some kind of a rights regime. So my off the cuff answer is that the receiver rights approach is probably not going to work here, whereas maybe thinking about the application, the rights based on application requirements might be a better option to think about to address this problem, if we are able to identify where this is coming from. I hope that answers your question. I don't know.
Certainly, in some ways, I really just wanted to raise it because I just know it's going to be a factor. However, if there's anything that we can do to help to support your discussions from people inside of really the meteorological community who can speak more to their expertise in really doing the satellite data assimilation, to then be able to do their QA QC process to really determine why they choose to throw out certain data because they are concerned it is contaminated versus when they don't. Being that I know that they have certain measures of that, but again, part of it is that gut feeling of sort of like taking a look at the overall data and saying, this doesn't seem quite right based upon past trends. And so not exactly a clear answer for really the economic folks. Thanks.
Thank you, Renee. Thank you for bringing that up.
Great. I want to sort of echo. So it's Scott Palo. I want to echo Rick's comments. I mean, I think it's great to see Flagship 2, up and running, getting momentum here. So the question I'm going to ask is about the overall arc of the program plan for the next year. We heard sort of from the separate areas. I'm kind of curious, do we have specific, targeted goals in the program plan? And I think, learning from Flagship 1 was, putting some stakes in the ground with the workshop in November and the workshop in June, and going to the field really drove development. And I guess I want to know, are there thoughts on the program plan and thoughts on sort of anchoring some whether it's experiments or other elements, workshops with Flagship 2? I don't know, Mary, you want to take that?
All right. So I think there are places that there's clear kind of milestones. I mean, one of the ones that's very clear on the weather radiometer side is we really get one shot at our initial weather simulation because the numerical weather models take so long to run. So, clearly we need enough lead up and enough examples of risk simulations to pick a really relevant example. So I think that, we probably need to have some sort of sprints before we get to the point for that. On the experimental side, I think that there are opportunities for us to go in and look at some specific things. For example, there's an aspect of discovery. Let's go survey and find what's there. Some of what Al's doing is like that. On the other hand, we may also go, Al, on your way, there's a 24 gigahertz system here that we know about. Can you go measure the harmonics, for example? So I think we do structurally have to, in like this drive around the country milestone plan, it would be great if like every city there's a target for Al's team, for example. And when they get to MIT, we might be able to do something joint, which was always, we'd already planned and talked about that, for example, that we otherwise couldn't do. So I do think that there's an aspect of trying to structure things like that. It's definitely not as experimentally driven a work plan. Flagship 1 benefits from, we're going to do an experiment and this is it. This one, part of the difficulty here is actually that the scope is way beyond what can be initially done. We're going to evolve the simulator initially to solve the simulations we need for these particular impact areas. That's by no means the limit of what one could do with these simulators or how you could extend them. So now what was interesting, so that's, I think that's, it's a good point that we should look at like workshop targets or milestones like Al gets on the road. Here's the milestones along the way. What are we going to do? The other aspect is things like, where would it make sense to have map measurements, for example? as part of this. It doesn't necessarily have to be Al's team. It could be any of our SpectrumX team that we want to pull in who happens to have a MEP and is going to be involved in this. So I think your point's well taken, that we want to milestone this pretty well. I think that that's some of the stuff that can be discussed tomorrow, actually, in the flagship work element lead discussions, because that's the kind of thing that we've now got work element plans. People are executing. Money will eventually get to them properly as bureaucratic lag allows. And it really comes down to, we have 1 year kind of. Some stuff's obviously been going on longer, but we've got kind of 1 year to get a really good impact and result. Ideally, Flagship 2 is one of these things I see going into a renewal most likely, because it's such a robust area. And honestly, it's an area NSF has the most skin in the game for. So I guess that's my perspective on it. And you're right, it's sprint-driven stuff pushes stuff forward, as we've found. And so, it's something for us to think about how to incorporate that effectively.
Yeah, I just want to add that for the moment, the big experiment are these weather model runs. And so we're going to talk through the schedule for that tomorrow, and that's going to be a big driver for getting Risk Sim to the point where it can do the kind of simulations we want to give the input that's needed.
We have one more. Ali has a question as well.
I have another question for Frank. Sorry for making you talk again. But I make it easy. Just give me a number between 0 and 100. What are the chances, despite all of these efforts for RFI mitigation for radio astronomy, in 10 years, radio astronomy is pretty much doomed if we want to do it from Earth? Give me a number between 0 and 100.
Don't bring out my natural cynicism. So I will say, I believe we are likely to light the sky up at a whole range of frequencies with all kinds of harmonics and inadvertent emissions. We already know that we see scatter with Westford at the hydrogen line off radars from the ground that are malfunctioning. So we discovered a Cape Cod radar that's got a problem because we saw it bouncing off Starlink. And we were like, where the hell is that coming from? So what's going to happen is we are going to enter an era where radio astronomy on the ground is challenging. Okay, obviously the beam avoidance helps. It gets you an extra 40 dB. So the companies that are participating in that are helping us, and they're buying time for the rights and policy and the technologies to catch up. All right. I do think that there is the potential, if we're overly aggressive on reallocation and bands, of what you could think of as a temporary dark age, and where many kinds of things we might do with radio telescopes become hard or even impossible. On the other hand, I think that'll force us to address some of the issues. And I don't see impossibilities, I see challenges. On the other hand, there are big investment questions, say from radio astronomy. If you look at the US, we didn't really participate strongly in square kilometer array. The US answer to square kilometer array, well, actually we were involved in the team at MIT. We're the only place, but we can't use it really. But actually I think we might be at Haystack still, but we'll have to look. But anyway, the bigger picture issue is US's answer to that is next generation VLA. 1 to 100 gigahertz spread across New Mexico, all of the central United States, down into Mexico, right? And really with some outlying stations to do incredible interferometry and imaging. That's a lot of money to invest. Will it actually work? I don't know. It's the kind of thing I'd love, when I look at risks, like for the astronomy case, what do I really want to get us to simulate down the road? I want to simulate NGVLA down the road. Now, we might not get to it this year, right? I think that's a stretch for where we're at. On the other hand, being able to say, if we do NGVLA and we have beam avoidance and we have side lobe cancellation, you'll still be able to do radio astronomy, and here's the impacts. That's very enabling. Or you can say, these have to be different, architected differently. They have to have phased array feeds, for example, that can avoid Starlink or avoid, different constellations. So that's the kind of thing I think we're in a position to make enough progress on to start answering some of those questions. Similarly, like the work you're doing on all sky monitoring, what I'm having Daniel, there's an aspect of this down the road where risk sim is not just, like I'm going to model and predict some basic cases and some, at scale, but nevertheless, you look at it but it becomes an assimilative thing. What do we see in the sky? What do we predict is going to be there? Is there a difference? And it's very important to realize that, the US is the leader and intends clearly to be the leader in mega constellations. But other countries are going to build these. And not all of them are going to be like, SpaceX and Kuiper and AST Space Mobile, talking to NRAO, working cooperatively, working with zone management. So we may find that it's not really the US actors that cause necessarily the problems. It might be other actors. Or we may, internationally need to create a framework they're willing to participate in. That's a rights and policy question, right? That's how do you do that? How do you make them feel that they want to be included and want to be kind of the responsible citizens we'd all like everyone to be. So
thanks for not giving me a number like ChatGPT.
you don't want to know my number.
Frank, this is Rick. I just want to say something. I've been watching, the meteorological guys and the radio astronomers, since about '97. And I'll be honest with you, most of it to a guy who was building stuff that would interfere, it was just arm waving. What you're doing, you're going to have real data and a real story that's bigger than arm waving. And this is huge to me because you're going to have like real data, real models. Not, oh no, we won't be able to tell where the hurricane went. I mean, because to be honest, that was the kind of stories that I've heard for a long, long time. They didn't have a lot of data. That's gotten better over the years, but I think this is going to be great. You're going to actually have a technical, real data-driven argument to make on these things, and I think that's huge.
That is the goal, and the goal is to at least statistically validate it. One of the things we already realize from the early measurements and modeling is that many of the constellations don't provide enough information for perfectly accurate modeling. You don't really know what Starlink's beams are doing as a function of time. Now they've actually offered to run the simulator and parameterize it and tell us a result, but they won't tell us what they did, right? So there's a transparency issue that starts to come about with that approach. And this is a motivation for policymakers, is we do not have enough information to accurately and responsibly model these systems that are being deployed at scale. And so asking us what the impacts are going to be, we're missing the pieces to do the simulations efficiently. We're missing the pieces to tell us the parameterizations that go into it. Underneath it, we know the physics pretty well. And there's another step like to put water vapor in for 50 gigahertz and other stuff, which makes it very challenging. But yeah, my take on this was very much go after it as let's go look, let's predict and see what we actually understand and what we don't understand. And then we can iterate. And it's experiment-driven approach, but it's good science. It's model data comparison. And if you don't understand it and you aren't actually accurately modeling it, you're missing something.
All right, thanks everybody. It was great to have all the discussion and questions. I hope I will see many of you tomorrow afternoon when we really get to dig into the schedule and experiment planning for FP2 in the next year.